All right. So standard announcements, homework D2's out there. It's a little calculus, a little algebra on this assignment. 2 questions related to random variate generation, which is something we'll see a little bit in this lecture and then also in next lecture. Just to come some tips. In the first one, when integrating from going from PDF to CDF, you're going to be taking this integral right here from -infinity to x in the CDF. Remember to break that up along wherever the boundaries are if it's a piecewise PDF, and you'll see what I mean by that. So in other words, if I've got a PDF that's got a piece that goes from -infinity to 0 and another piece that goes from 0 to some higher number, if I'm integrating to something above 0, then I have to take the integral of the lower piece through its whole range plus the partial upper piece. So hopefully that'll make, I think, more sense when we talk about it directly next lecture, and then hopefully will start to make sense as you guys start doing that problem. So sorry, let me just see if I can get some more light up here. Okay. So then the other question is the second one, where you have to invert a CDF to get a random variate generator. And one of the things that you have to practice here is when you invert a quadratic, deciding which root to take. So remember that, when you take the square root of x squared, you either get the positive square root or the negative square root out. And either one is equally legitimate. So you have to make sure that you choose that one based on the sign of the variate that you actually want to generate. And that's something that we'll go over again next lecture, but that's the trick to look for in that second problem. So that's technically due the day of lecture E2, but again, we've got that 4-day grace period. And then right after that grace period, the solution set will get released. The other thing is this one does ask you to actually generate, I don't know, 1,000 or 10,000 or whatever values of these random variates, and then generate a histogram. Don't just submit a spreadsheet with thousands of random realizations. And so you're supposed to, submit kind of a document that is compact and concise, that summarizes your results with plots, graphs, like a histogram, with proper axis labels, proper scaling. So try to think about like what would be useful to you if you were to read this thing. The grader is not going to go through a spreadsheet and check all of thousands of lines. Also, you shouldn't take your thousands of lines and just paste them into a Word document, because that's sort of even more useless. So, so the goal is to say, like, how do I, you can, in theory, this homework D2, your solution to this, the document you get to solve both problems could be 2 pages long. It shouldn't be 30 pages long, just lists and lists and lists of numbers, because that doesn't really help us. Now, I think I might ask you to also upload, sort of in the spirit of showing your work, you might upload that spreadsheet as an auxiliary file to the submission, but the main submission, the main thing that the grader will be grading will actually be that one document, which should only be a couple of pages long, not 30 pages long. There's also now ICA-F is available. This is a midterm review ICA. I've talked about this a couple of times so far. You can take this ICA over and over and over again, and you'll get the highest score. It randomly samples from all the previous ICAs. It's worth at least 3 times as much as the normal ICA. So if you do it, it'll actually buffer your score. So this is one, of course, you can use as one of your ICA drops, but if you don't use this one as an ICA drop, it's probably a wise choice because it helps you practice for the midterm, and it's got a bigger score, and you can take it as many times as you want. So again, it's got that buffering effect. The midterm, I'm kind of hinting at here, is coming up soon. It's we're going to have basically lectures E1 and E2. This is E1. Then I guess today's Thursday, so then Tuesday will be E2. And then a week from today, lecture F is a midterm review lecture. So then the midterm comes the week after that. So, so basically 2 weeks from last lecture will be stage 1 of the exam. 2 weeks from today will be stage 2 of the exam. So stage 1, closed book, closed notes, totally individual. It's the Canvas-based exam. You can take it in here, but you don't have to. It's a timed exam. Once you start taking it, you'll have 90 minutes. Stage 2 is a open book, open notes, and open collaborator exam. So you can use students in this class section. You can come here during that day, but it's also Canvas-based. It's not timed. And you can actually submit it multiple times. So if you do submit one time and think, oh, shoot, I actually want to go back and change my answer, you can submit it, but we'll grade the latest submission. So not the highest, but the latest. And then otherwise, the other reminders is that now that we're after the Lab 5 on, we're working with ARENA. And so most of the ARENA labs will be based in some part on an exercise that starts in the book. And so, so you have to have access to that Kelton et al. Book, 3rd edition, or really, I'd say 4th edition, probably 3rd edition or higher should be fine. And again, I give you some resources on Canvas that should allow you to make use of that, even if you don't have a copy of the book yourself. So any questions about the schedule moving forward? I guess I should also mention on that midterm that if you take the lockdown browser compliance test, which is like a 1 question, just like it just confirms that you're able to run lockdown browser, that will unlock the midterm module, which will allow you to get access to the midterm when it becomes available. But you also get access to past midterms from previous semesters, a practice midterm that you can take on Canvas as many times as you want, and other resources. So if you're looking for study resources, then get that compliance test out of the way. It'll unlock that midterm module, and you've got all of those resources. Okay, questions online? The date of the exam, I don't want to quote dates just because on the spot I might get them wrong, but so the question was, the date of the exam is October 3rd, correct? And the date of stage 1 will be a week from this upcoming Tuesday. So whatever that math is, if that's October 3rd, it should be that not this upcoming Tuesday, but the Tuesday after that. So check on Canvas, all those dates are there on Canvas. And I think I expanded the availability for stage 1. I just off the top of my head, I don't remember which way I expanded it. So I think I give you, for example, Monday, Tuesday, and Wednesday to start stage 1. So so you'll, as long as you turn it in during that availability window, then you're fine. And then likewise for stage 2, I think I gave you something like Thursday, Friday, and Saturday for stage 2. It might only be 2 days. I'd have to double check. I forget for this class whether I give you how big I give you for each one of those stages. But if you look at the availability windows for stage 1 and stage 2 in the midterm module, you can see that there is some flexibility on when to start it. But you definitely have all day that Tuesday to start stage 1, and you'll have all day that Thursday. I think I give you a little bit more time. So like the Friday after and maybe the Monday before. So double check on Canvas to see the availability windows. All right, so any other questions? Oh, and so on chat, she said, okay, the 4th, thank you. So apparently the Tuesday is the 4th. But it if you see the 3rd as the availability window opening, that's me saying, well, I'm gonna give you access to it. And still, if you start it, you got 90 minutes. But it's formally, due on whatever that Tuesday is. All right, great. Okay, so what we were talking about last time is, we're getting into input modeling, where we're picking the probabilistic models for things like inter-arrival times and models for things like demand distributions and inventory models, and so on. So we need to pick, there's a bunch of probabilistic models out there. How do we pick them for each one of the small scale phenomena that we add up together in our sim to give us the big phenomena? And so we went over a bunch of them last time. So we basically went all of the ones in this continuous box, and I'm going to do a quick review of the ones in this discrete box, at least the green ones here, as well as the Poisson process before we get on to random number generation. So these ones that are not gray, like uniform, triangular, normal, exponential, Erlong, Weibull, Poisson, Bernoulli, binomial, negative binomial, and geometric, and the Poisson process, these are all the ones that you should have familiarity with. You don't need to memorize PDFs or CDFs. But if I were to ask you about a flexible failure distribution that can be made to fail more or less often than just random chance, then you'd say, okay, that's a Weibull distribution. You know, if I were to say a failure distribution representing the sum of independent exponentials, that's an Erlang distribution, and so on. So, you know, just a general idea of what are the basic cases for when you would use each one of these. Okay, so let's pick up where we left off last time, just to knock out the ones that were left over. And I've gone through all of the exponential based ones. So if I were to go back here, exponential, Erlang, Weibull, and Poisson are all related to each other. That's why I've got them in blue here. And so these green ones, just like these blue ones, are all based upon an exponential in some way. These green ones are based upon a Bernoulli trial in some way. And so this is the classic kind of Bernoulli trial from when you first are introduced to probability. It's basically a weighted coin toss. So a Bernoulli trial, you often would not use this to model anything, but you'd use a distribution based on sequences of Bernoulli trials. So a Bernoulli trial itself is just a random variable whose outcome is either going to be 1 with probability p or 0 with 1 minus p. So you can think of it as heads or tails, but you can adjust the fairness of the coin. So if p is 0.5, then it's a fair coin that comes up heads or tails equally as often. Its CDF looks like that. So it's 1 minus p for pretty much for everything for 0, and then it's 1 for 1. So it just has little steps. So the mean value of a Bernoulli trial is just the probability, so that's convenient. So if you flipped 100 coins and you took the average outcome of that, then it would give you the probability that each coin individually came up heads. That's all I'm kind of saying here. And this variance expression, I'm not going to ask you to memorize that or whatever, but when we start talking about confidence intervals for proportions, you'll see this square root of this thing. In other words, the standard deviation of this pop up again. So it's just a good expression to start to burn into your brain, because you're going to start seeing it more and more as you look closely at other things in stochastic modeling, this p times 1 minus p. Okay, so like I said, fair coin toss, and we use it to build other probability distributions. So what do I mean by that? Well, so the binomial distribution is kind of a very common one here. So once we have a 1 coin, we can now ask questions about multiple coins. And when I say coin, for industrial engineers, I can just say, it's not necessarily a coin, but it could be, whenever I turn on a machine, how often is it going to fail that day? Am I going to get a machine failure that day? It's a discrete outcome of counts of failures. That's kind of what we're getting at here. So we're not modeling coins so much as outcomes that are either good or bad, fail or operational. And so we can ask something like, well, let's say I have n trials that could be failures or not, and they have a failure probability of p, so that's the weighted coin probability for each one of those trials. Then a binomial distribution tells me the number of, so for those n trials, it tells me the number of trials that come up successful. So if I look at a distribution down here, like these red dots here, p equals 0.5 and n equals 40. So I can see that this discrete random variable, it counts, it either goes from 0 to 40, it doesn't go any higher than 40, because it's only defined, like if I flip the coin 40 times, the most outcomes I can get is 40. But if it's a fair coin, then that means the mode means that 20 out of 40 are going to come up heads. But that's going to happen pretty rarely by itself. There's going to be a lot of outcomes that sort of stick around that mode, and that's what we're seeing here. So it's more often than not that I don't get exactly 20 coins coming up heads. I am probably going to get something that is maybe in between 20 and 30 coming up heads. That will be much more likely than just getting 20 exactly. And so that's what we're sort of seeing here. It's if you flip a coin that many times with a certain probability, what's the distribution of times that come up heads or come up failures or come up whatever your special event is. So with that, like the number of successes and a fixed number, there we can also start thinking about other things we might count. So not just if I know I've got 40, how many of those 40 come up a particular way. I could also say, well, what if I don't fix the number that I'm going to go at? And I really just want to know how many do I need to go until I get a particular number of outcomes. So how many light bulbs do I need to come off the manufacturing line for me to get 10 light bulbs that are failures, that are duds, right off the line? So that's something that if I know the failure probability for each light bulb, then I can sort of figure out that for this failure probability, this is the distribution of sequences that I can go until I get that many duds, that many failures, and not necessarily in a row, just over that entire time. So that's what I'm saying here. This is the modeling the number of independent Bernoulli trials until the Rth success. So those are successes or failures, whichever one you call them. It's sort of it doesn't really matter whether you call them successes or failures. If they don't have to all be in a row, but over this number, then we're going to get that many of them. So I think I don't have a plot of that, but the special case that we often talk about is when R is equal to 1, which is the number of times I go until I get exactly one success or exactly one failure, again, depending on what I'm modeling. So whatever the special event is, how often do I have to go until I get that special event? And that's the geometric distribution. So a geometric distribution is just a special case of a negative binomial. So those are things you just have to kind of start to memorize. Is if I go back, binomial is given and you can kind of use the parameters to help you. If I have a fixed number of trials, how many of those trials come up with whatever my special outcome is, heads, true, whatever. And the average of this thing is going to be n times p. On the other hand, here I've got the same probability, but now I'm saying how many of the special event do I want? And I don't know how many total I'm going to get. So I'm asking how many total do I need to go in order to get that many of the special event there? And that average is going to be R divided by P. So it's a little, they're very similar here. And the special, so again, from binomial to negative binomial, and then geometric is the very special case where we're only looking for one special type of outcome. And the geometric is the discrete analog of the exponential. So an exponential is kind of like if we just have a random failure probability, how long do we have to wait until we get a failure, until this aircraft wing develops a crack, for example? Well, this is just the discrete analog of that, where it's kind of like if I know every day I check the aircraft wing and there's a certain probability that I'll get a crack, then how many days do I have to go until I actually see a crack in the aircraft wing? So not surprisingly, the geometric distribution is the discrete distribution that also has this memoryless property. So the exponential is the fancy distribution that's continuous and memoryless, and the geometric is the special distribution that's discrete and memoryless. And but otherwise, so they have that very strong relationship there. Okay, so all of these that we've talked about here, Bernoulli binomial, negative binomial, these are all, and Poisson really, are all discrete. So these are all count. They all are going to have count outputs. So whenever you're describing a random variable, it's counting things up, you should be thinking in this family, Poisson, Bernoulli binomial, and negative binomial. So any questions about those before we do a quick overview of processes in the Poisson process? Does it make sense? All questions online? Okay. So the last thing that we need to really have in our modeling toolbox here is the Poisson process. Well, what is a Poisson process? We have to sort of unpack that a little bit. I've been talking about random variables. Well, there is another entity that's sort of higher order from that called a random process. A random process is an indexed collection of random variables. And what I mean by that, I can now sort of demonstrate through a special type of process called a counting process. A counting process is a family of their random variables, each one of them called n of t. So this is for all t greater than 0. I have a different random variable n of t, where that random variable n of t represents the number of, let's say, arrivals that have occurred by time t. So we can think about like, okay, so at time 0, how many arrivals might I have gotten? At time 0 plus 0.5, how many arrivals might I have gotten? At time 0 plus 1, how many arrivals might I have gotten? Each one of those questions is asking a question about a random variable. So at every time, you have a different random variable, and that random variable has its own statistics. And the statistics of the random variable at time 0 are going to be different than statistics at time 1 or statistics at time 2. So not one set of probabilities or distributions describe all of these random variables, but instead we have to have a way to sort of connect the index of each random variable to it's the parameters of that distribution. And so the Poisson process is one special case of that, where it is a counting process where what we'll get to here is that the random variable in the Poisson process is a Poisson random variable. And so it describes the number of counts that occur if you have exponential interarrivals. So formally what defines a Poisson process is that this is a process that, so normally associated with a rate lambda, that describes the count of arrivals when there are no simultaneous arrivals. So arrivals occur one at a time. They have what we call stationary increments. So that just means that the number of arrivals between any 2 points is only determined by the length of time between those points and not the actual time. So if you're saying how many arrivals occur between time 1 and time 5, that will be the same distribution as the number of arrivals from time 4 to time 8, because they're both separated by 4. So it doesn't depend on when the arrivals occur, just how long it's been since you've been counting. And independent increments. So the number of arrivals in non-overlapping time intervals are independent. So if you look at the random variable from 1 to 4, and you look at the random variable from 5 to 8, because those are mutually exclusive, then knowing how many arrived from 1 to 4 does not give you any information about how many arrived from 5 to 8. So technically that's all we need to describe a Poisson process. If we have that, then we end up getting those other definitions. So these are sort of equivalent definitions that can be derived from those properties just said there, that the random variable inside the Poisson process is itself a Poisson random variable. And that Poisson random variable is going to have a parameter, which will be lambda, which goes on with the process, times t of the random variable. So in other words, each n of t in a Poisson process represents the count of arrivals that have occurred since time 0. And so if we take the t that we're looking at, we multiply it by the lambda, then we get the parameter alpha, which will be the parameter for a Poisson random variable. We can plug that in and we would get the count. We get a discrete distribution, so a distribution of counts that have occurred since time 0. So that's why it's called a Poisson process, is that each random variable is a Poisson random variable, but it's a collection of them together, and that's why they're a process. Now, this is where it gets confusing to a lot of students, because a lot of students, I think, confuse the Poisson process for the exponential random variable. And the relationship is here, is that if you look at the time in between 2 arrivals, say of any 2 sequential events, any 2 arrivals, and you look at that distribution of time. So that in itself is random. That will be distributed as an exponential random variable with the same rate lambda as the Poisson process. So that is why we say a Poisson process is effectively the count of exponentially distributed interarrivals in an interval. But but there's 3 things being kicked around here. There's the distribution of the interarrival times. There's the distribution of counts in any interval. And then there's the process, which kind of collects all of those things together. So there's 3 things that we have to keep straight in our heads so that we kind of know what we mean if we ever say You know, where I want your mind to go when you think Poisson is Poisson random variable discrete. But if someone says Poisson process, then you should start thinking, well, that means both the Poisson random variable discrete and an exponential random variable continuous. They're all kind of collected together inside this Poisson process. All right, so this is something that in say 470, if and when you take 470, you'll talk a lot about Poisson processes and their interesting properties and all the crazy things that you can do with them in queuing networks. But we just need to know about them because they're often used to model the arrival processes that we see in stochastic modeling. All right, so any questions about the Poisson process? Might be old news to some of you. Pretty clear how those come together. Now, what you'll see in labs, yeah, I'm sorry, go ahead.
How random and like how often real world is it actually like Poisson process like that?
Right.
Like it seems like almost like a theoretical like out of that like proven evidence. Like how like applicable like are there a lot of applicable applications that really truly like that or just like the places?
That's a great question. So the question is, how realistic is the Poisson process? It seems like it's a mathematical ideal that sort of represents kind of truly random arrival processes or counting processes, and how realistic is that? And that's a great question. That's a question you should always ask whenever you start modeling things with exponentials and so on. It would say that this is a good first order approximation of generalities that are shared among different systems. So if I want to say, you know, how do I predict the queue of students that's waiting for me at office hours? And how does that relate to the queue of passengers who are waiting to get through the security lane at the airport? There certainly are very, like, you know, for example, students, there will be clusters of students that arrive at my office at the same time. Well, that violates the simultaneous arrivals assumption there. So that's not going to, you know, so technically there's a better distribution out there. Similarly, at the airport arrival process, but when the time people hit security, they've already gone through a bunch of other things that have spread them out in a very kind of uniform way. So in reality, there's probably not like things like independent increments. And so, you know, as I start seeing that people start coming more quickly, I can probably predict they're going to continue to come more quickly. So, so this is sort of like where we start. And then we have to sort of ask ourselves, all models are wrong, but some are useful. How far does this get us? And if we have to start varying the arrival assumptions, does that change our simulation results qualitatively? If it does, then we need to go and find a new arrival process. But this is, I would say, sort of the most honest way to start. Because if you come up with any other arrival distribution, it's most likely just sort of picking parameters out of the air and out of your own biases. And so if we start from here, we can say like, this is kind of like our null. And then after this, we can sort of build up on top of that. Yeah, and so actually going along with that, that's sort of last point here that you'll see in lab 6. So this Poisson process is what we call the inhomogeneous or non-homogeneous, the homogeneous Poisson process, which means that this lambda is constant throughout. Now, as we'll see in lab 6, you can simulate systems that have arrival rates that vary throughout time. So, and this makes sense for like an airport or whatever. People arrive at the airports very differently from 9 to 10 than they do from noon to 1 or from 4 to 5 or so on. So what we often can do is assume that the arrival rate is mostly constant for short periods of time, but then have steps in that arrival rate which change, or we can even have the arrival rate change relatively continuously. Now, in order to estimate, or to generate simulated inhomogeneous Poisson processes with changing arrival rates properly, it takes some extra machinery that fortunately has already been built into ARENA through its scheduling facility. So in lab 6, rather than you having to figure out how to generate inhomogeneous Poisson processes with changing arrival rates yourself, you'll be able to tell Arena, here's my schedule of arrival rates. And so in my simulation from 1 to 2, I want this arrival rate, from 2 to 3, this arrival or whatever. And it will figure out how to deal with those ugly cases where the slow arrival rate from 1 to 2 might generate someone arriving in the fast arrival rate period from 2 to 3. And it will sort of know how to deal with that so that it doesn't create a lot of edge effects in a proper way. So that's already been built into Arena. So that's the simplest way to deal at this level with inhomogeneous Poisson processes or time varying arrival rates, is by using scheduling facilities inside Arena. We'll do that for you. So hopefully that makes sense, is that Poisson process is a great place to start. The next variation of that is to have time varying arrival rates. And then after that, we can go, varied other sorts of variations. But if you've got no other information, you may as well start with the Poisson. So like I was mentioned before, I'm not going to go into all of these details because they're really kind of 470, but you can split Poisson processes by probability, and you end up getting more Poisson processes out. And you can merge Poisson processes and you get more Poisson processes out. So they're really cool processes in that if you start with a network of Poisson processes, you can sort of keep the Poisson assumptions all throughout the network, which is one of the big reasons why we use them, is because they're tractable as opposed to other distributions that aren't. So I've mentioned, like in Kendall's notation, MM1 Qs, this notation, Kendall's notation, this M Markovian arrivals or memoryless arrivals. This is basically saying arrivals occur according to a Poisson process. So, this, whenever you see an MM1 that somebody says this is MM1 queuing node, they're implicitly saying that they're going to use a Poisson process. And like I said here, there are relatively few assumptions. You can add non-stationarity. They've got some cool mathematical properties. So those are some nice strengths. If you want to learn more about how to use the Poisson process stuff, which again is more sort of closer to 470 type stuff, then you can read through chapter 6 in this class. Because we saved that for 470, we kind of skip over that. But if this is something that interests you, then I recommend just flipping through chapter 6 and seeing what they say about queuing networks and Poisson processes. So that's all that I wanted to cover from last time. Are there any questions about any of these random variables or these distinctions? Yeah. That is something that I don't want to say you can only do it with Poisson processes, but I feel like I would have to do some research to see if I can use the only qualifier there, but it is very rare for you to take an arrival process and another arrival process and split them or merge them and get the same type of arrival process out. And so what I mean by splitting and pooling is if somebody comes to if somebody we know comes up to a document checker in an airport and 30% go one direction and 70% go in the other direction, then that's what's called a split process. And so the arrival process coming out of the 30% side will be Poisson, but it'll have 30% the lambda, 30% the arrival rate. The 70% will be Poisson, but it's a lambda will be 70% of the incoming lambda. And likewise, if they get merged back together, then those arrival rates will get added together and you'll get one process out that will be Poisson with the sum of those. And so all of the arrival rates just end up dividing up and then adding back together in the networks. And that is a special property that I think is going to be unique to Poisson processes. It's certainly, if it's not unique to Poisson processes, there's very few other processes that have that nice ability to be split and merge and split and merge and stay in the same family. Okay, any other questions from here or online? All right. All right, so kind of get the summary of like all of that stuff. Stochastic approach uses randomness as a source of variation. Input modeling is how we choose which random list to use. So we're going to focus on how to actually evaluate our choices after the midterm in lectures, basically in Unit G. This is sort of a cheat sheet for the continuous and discrete distributions. So I've kind of like put down here with the ones that I think you should know for this class, and it's a good starter pack for stochastic modeling in general. And I kind of given a little description for when you might use these and listed the notation that is typically used for them and the parameters. And these are sort of ones that I think are more advanced. I'm not going to require you to know for this class, but they're good to know for the future because these are also very commonly used in stochastic modeling. Same with discrete. These are the discrete ones I want you to know for this class. Basically, when I ask you, say, what do I want you to know for? I really want you to sort of know everything that's on this page here and everything that's on this page here that's not this gray one here. So for each one of these, you've got the name, you've got roughly what it's used for, and you've got the parameters and its notation that it's kind of used to denote that you're using that distribution. So, that's where we were from last time. So moving into the new stuff. So any questions about any of this before we move into drawing random numbers? Okay. All right, so once we select a probability distribution, how do we actually get the computer to generate that probability distribution? This is another way to say that is how do we sample from a desired distribution? So the example we have here is, let's say I have a lifetime of a device that expects cracks in an aircraft wing and the failure times are exponentially distributed. Well, okay, so I've picked an exponential for the failure time. How do I get the computer to generate said exponential out of here? So I know from last time that an exponential has this probability density function. I know that if I take the area underneath that probability density function, I'll get a cumulative distribution. And that cumulative distribution for an exponential looks a little bit like this, and it's written out here. And so what I talked about last time, and what we'll talk about in next lecture in more detail, is that if I draw a bunch of uniformly distributed random numbers between 0 and 1, if I assume those are available, the same way in a board game, you assume you've got a fair die available to sort of guide the rest of the game. Then if you take those numbers and you put them in the inverse CDF, so you're kind of running this function backwards, then the uniformity here gets stretched out along the x-axis so that the resulting distribution of numbers you get out of that function is exponentially distributed as desired. So that's great. So once we learn how to take these inverses, then we should be good, assuming that we have this source of random numbers. So that's really what we want to tackle today, is where the heck do we get those random numbers inside a computer, which otherwise is deterministic. So it's kind of going into this, John von Neumann, one of the sort of founders of modern computing, and a bunch of other things, had this quote, who's also sort of present when they started working with random numbers. Anyone who considers arithmetical methods, or in other words, computational methods of producing random digits, is in a state of sin, which I thought was interesting because historically, some of the first people to come up with random number generators were actually friars. Sort of one of the things they were hanging around doing is coming up with some of these early methods for coming up with randomness. Now, before sort of modern computing, there were sort of interesting ways that people kept track of random numbers and disseminated their use to others. So you can even go onto Amazon and you can find a small book of random numbers. And so this time it was 15 bucks, you could buy this thing. And if you open up this book, it would have lists of these random numbers. And so you'd have 3 different columns that were sort of guaranteed to be independent from each other. And so you could choose, all right, I'm going to start column A, row 10, and I'll just keep moving down here. And I've got a list of these random numbers. If you put a decimal in the front of these, you can think of them as uniformly distributed between 0 and 1. And so this actually used to be a way that you would generate a lot of random numbers. You could go to the library and read these CRC texts on random numbers, and there would just be pages and pages and pages of numbers that someone had pre-calculated when it was very difficult to calculate these random numbers that you could then just use off the page. So that was sort of one way you could generate these random numbers. Now, fortunately, we can go into Excel and we can type rand, or we can go into MATLAB and type in a number of different rands, and we can generate random numbers in a bunch of different ways. And those are using these arithmetic methods. And so they're using math to generate these, not flipping it up into a book. And so we have to sort of ask, can we trust that these are random? So that's something that we need to sort of deal with. So how do we even evaluate that a random number, a pseudo-random number generator, generating random numbers between 0 and 1 uniformly is reliable? Like, we have to think, what are the two properties that we would care about? What are the properties we care about? If we think about a die roll, I think we can come up with sort of two properties that really matter. Like, for one, we care about whenever we roll a die. Well, how about that? So what do you think would, if I want a reliable die roll, like a reliable 20-sided die, what do you think are properties that I need for a 20-sided die in order for me to bundle it in the box and ship it out with the board game? Any ideas of what are good things to have in a die that I'd have in a board game? What are properties? Yeah. Evenly weighted. So I think you mean like it'd be just as likely to get a 20 as it would to get an 11. That's sort of right? Yeah, so uniformity. That's one of the things. What's another thing I might want out of a die? So I roll it, and over 100 rolls, I get, I get every side equally often. But what's another thing? It's like, if I roll a die and it comes up 15 for me, and someone else rolls a die, then what do we want about our two die rolls? It's a relationship between two die rolls. Independence, right. That's what I'm looking for there. So those are the two properties that I'm gonna want for a fair die. I'm also gonna want those for my random number generator: uniformity and independence. So, uniformity, what do I mean by that? That means that each random number is approximately from a uniform distribution between 0 and 1. So if I divide the interval up into n subintervals, the expected number of numbers that fall into each interval is the number of die rolls divided by the number of intervals. That's what I would expect to be the case. So, or there's an equal probability to see each face of the die. So I've got kind of example, a good set of rolls from this die. So if I look through this good here, pretty much every number is represented equally likely. But then if I compare to this bad, then it looks like 2 is coming up a whole lot and 7 is coming up a whole lot, maybe 3, but I don't see really any of the upper numbers. So this is what we would refer to as a violation of uniformity. So like on a midterm, I might give you example outcomes from a pseudo-random number generator, and I'd ask you, and you'll see this on the samples, does this violate uniformity? Does this violate independence? And I want you to be able to spot it when you look at it. And that's, it's hard to do because random numbers, sometimes you really do get a bunch of heads in a row. But I'll, on a midterm, I'll try to make it pretty obvious. And I would say, like, this example is pretty obvious that over this long many of runs, I don't get anything greater than 10. That seems a little strange. And I get this many repeats of 2. That seems a little strange. So this violates uniformity for sure. So any questions about this definition? What I mean by uniformity? Questions online? Oh, yeah, thanks. So online, there was an answer about independence to be independent. So thanks. That was the answer I was looking for there. All right, so then the other thing, then, independence. That's the other property that we need. And so this, we can say that if I have 2 random number draws or 2 die rolls, we want them to be independent. So the probability of any value from one is independent of whatever values came up for another. So if I think about this in terms of my die roll, this one down here is good because if I look here, like for a 20, it's followed by a 4. If I had another 20, I don't know if I have any repeats here, but there's no patterns that are obvious here. It's not like I can see that, oh, well, they threw an 8. And so I can definitely tell that, the next numbers are going to be 16, 17, or 18. I can't really tell that by looking at this. It looks like there's an equal chance of all 20 to be drawn, regardless of what was previously drawn. I can contrast that with this bad here. Here, all 20 numbers are represented, so it is uniform. It does not violate uniformity. But there's a clear pattern that if I draw a 1, I'm always going to get a 2 afterwards. Likewise, after a 2, a 3, and so on. So this is what I mean by violating independence. This is uniform, it's just not independent. So any questions about that distinction? So of course, we need to rigorously, come up with tests for these things. objective tests. So we're not just staring at them and kind of making a judgment call, but we need to sort of understand the salient features of these two properties, uniformity and independence. Okay. All right, so that's what we need to do, is we need to build tests for those. So, all right, let's see what we get towards that. So methods for generating random numbers. Well, talk about throwing dice a lot. That's great, not really practical for a computer. Drawing from a shuffled deck of cards, drawing a ball from a well-stirred urn. For some applications, sure, that's great. Probably not good for drawing thousands to millions of numbers in a computer. There's even things like hashing of physical processes. So there are websites out there that have cameras that are fixed on lava lamps, and that generates a unique pattern. And you can take all of the pixels of that and turn them into numbers, and then use a formula based on those numbers, and it will generate one number from every image that's based on sort of that, and that's referred to as a hash. It's a one-way function, so for every, so there might be multiple numbers corresponding to several images, and that will sort of taking randomness in this two-dimensional, multicolored physical world and turning it into randomness in a number. And in theory, you probably could set that up on the web and generate streams of numbers, but this image changes so slowly that you probably are going to violate independence if you used that at a high rate. So there are other options that are very similar to that are a little bit more practical. So if you go to random.org, a lot of my empiricist friends, when I set up experiments in the real world, they randomize using random.org. It's a standard method. And random.org actually samples from atmospheric noise. So it goes out and it sees pressure variations and temperature and those sorts of things. It turns those into random numbers. And it can generate a large number of very uniform, it can generate uniform randomness, and it can do it at high throughput with very few violations of independence. So in theory, that's maybe an option, but it's online and need an API for it. So it's just, these are all maybe get to sort of what we would want in the ideal. They're not super practical, like if you're not online and so on. So what we would like to is have something that is not only uniform in independence approximately, but we need something that should be fast and easy to sort of calculate without being connected to the internet. It should generate sequences of random numbers that may repeat, but they repeat after very, very, very long cycles. And we actually know that computer generated sequences, mathematical generated sequences, will always repeat. That's just necessary. And given the same starting point, which we're going to call a seed, they generate the same sequences. So this is the idea that if I have sort of 5 die rolls, if there's a way for me to reset the die and roll it again, I'll get the same sequence of numbers out. Now, why might that be useful in the computer simulation context? We have an idea of like, why would I ever want to reset my simulation and get the exact same simulation out instead of just running the sim and always getting a new sim? Let me see if there's anybody else. Any other thoughts on why would it be useful for a simulation to run? So I run the sim, I see from my airport, I get a certain performance criteria. Maybe I run it again and I get a different performance criteria, but then I want to go back and I want to rerun that first sim again. Why would I might want to do that? Any thoughts? Go ahead. Well, so there could be some interesting statistical tricks that we could do, sure. There might be just something less about the stats, just more about learning about the system. Like imagine if you could, you're looking at an airport and there's a terrible backup at the security line on Tuesday at 4 p.m. And eventually, they deal with it. But then, afterwards, they look back at it and they say, what the heck happened? And, you can't go back in time in real life. But what's interesting about the computer simulations is that you can. If you run a sim and you get a really interesting outcome that happened totally randomly, it might be a rare outcome, but it's a rare outcome, but it has a lot of what we call statistical leverage. It's really weird. It's really out there from mean to mean, but it's so bad that if it ever were to happen in real life, it would be a major problem. And we might want to say, we want to prevent that from ever happening. Let's further investigate that. We can then go back and tell the computer to rerun that exact same set of random numbers again. And we will see the exact phenomena run again. But we'll be able to maybe measure things we weren't measuring before to better understand exactly what happened. Or let's say we want to report it to somebody else. We want to tell our boss that, hey boss, it turns out I found a really terrible failure case. And I can tell the boss, can you run this simulation with random number seed 1452-636? And the boss just puts that in, and they can immediately run my sim and see what the case is. So I can very quickly communicate an entire timeline just by giving a random number seed. So it allows us to index universes. That's really what we do when we do stochastic simulation, is we simulate multiple universes in parallel that could happen, and we give them a number, and those numbers are the random number seeds. And so when interesting things happen, we can tell people which universe to teleport to in order to investigate the system further, just by telling them which seed we used. And so that's something that we would like to build into our random number generators, the ability to index randomness by seed. All right, so with that in mind, Excel kind of has this downside that unless you're using Visual Basic, it doesn't give you access to its random number seeds. So this is frustrating whenever you run a sim. If you get an interesting output, an interesting plot or whatever, if you save that and then say, I'm going to reopen that later, when you reopen Excel, it will usually just redraw random numbers. So like these are the two same spreadsheets, but I just maybe saved 2 minutes later and I got a different set of random numbers at the instant I saved. So I can't force Excel to use a certain seed. Most simulation tools actually allow you to specify the seed. Arena allows you to specify the seed. NetLogo allows you to specify the seed. And that allows you to, if you do come up with a particular run, to replay that run later and do further investigation. So how do you do that in Arena? You'll see this a couple of different times, but there is a seeds element that when we talk about elements in one of your labs, you'll get into, and you can pull in this seeds element and you can add a bunch of seeds that you can tell Arena to use. And the default random number seed is 10. So if you add a seed here named 10, you can actually change its seed value to any 5-digit number, and that will automatically force your simulation to use that for all of your random number draws by default. So this allows you to control the random number seed so that you can regenerate these sort of universes over and over again, and you can kind of control that. So this is an example that Excel doesn't have, but Arena does have the ability to set the seed. So that's something that we would like to have the access to, and any modern simulation tool allows you to set the seed for those reasons. So any questions about that? The desired properties of these random numbers and these seeds. Okay. Questions online? All right. Okay, so how do we generate these things? So there's the early attempts, like kind of coming out of those Franciscan friars, was this so-called middle square method. This was reinvented by John von Neumann, hundreds of years later. And it was a bad method, but it was a good start. So the idea here is my seed is a 4-digit number. I take I start with this 4-digit number, I square it to produce an 8-digit number. If it doesn't get to 8 digits after squaring it, I pad it with zeros. I set my next number to be the middle 4 digits of that 8-digit number. And then the output is going to be whatever those middle 4 digits are divided by 10,000. That will give me a random number between 0 and 1. And then I just iterate doing that same process over and over again. And so that was their first attempt at generating hopefully uniform and independent numbers. And so here's kind of an example that shows you one of the possible problems with that. Is you start out with this seed 5197, you square it, you take the middle 4, you get your random number. If you then start iterating here, then you can end up getting this degeneration to 0. So in other words, once the middle 4 hits 0, then you get stuck at 0 forever. And it's not that hard to end up getting these middle 4 coming down to 0. So that's one of the problems that you have. Other problems is that you can degenerate to other cycles very quickly, other short cycles. So if I do 6500, I square that, I get a bigger number that has 2500 in the middle, I square that, I still get 2500 in the middle, I square that, I still get 2500 in the middle, and so on. So now I'm stuck and I only get 0.25. So I don't really get, here I've got this sort of, this kind of decays with the pattern here. So I kind of violate uniformity and independence here. Here, I violate uniformity, technically not independence, I guess. But so neither one of these are good examples here. And there's a bunch of other sort of, yeah, question?
So if you have these numbers and one, how do you ensure that the number is random? And if you have only likely less than 10,000 possible, or I guess likely less than 9,000 possible,
Mm-hmm.
isn't there a finite number of ways to go essentially?
Yes, so right. So the questions are, how do we choose these seeds to be random? So that's one of the downsides of middle square method, is that some seeds are better than others. A good pseudo-random number generator, you put any seed in, you get the same qualities out. And so here, you could argue this seed might be better than this seed. So that's another example of how the middle square method is kind of poor here. And yeah, you are going to get cycles. I mean, if the outputs here are always 4 digits, then the longest length cycle I can have is 10,000 numbers long. Because whenever I get the same, whenever I get 0077, well, that's going to end up generating the same numbers. So like I'm doomed to, whenever I hit the same number, I'm going to get the same output after it. So yeah, I do have a cycling problem where I can't get any longer than 10,000. So I would like a random number generator that generates long cycles that I can start with any seed and have the same properties. And we'll get to that. That's the one that's coming up. That's LCG, or CLCG. But middle square just ain't it. So middle square was an attempt at that, but you were limited in your choice of seed, and even with and there were very few good seeds to choose. And this is just me kind of demonstrating those things too. So here's some examples where you start with one seed, things start to be going okay, and then you get into these short cycles. And then this one here is kind of particularly deleterious and kind of insidious. You start with a seed, and for a while, for the first 83 numbers, it actually looks pretty good. There's no cycles, things are bouncing around, they're pretty uniformly distributed. But then suddenly out of nowhere, you get into this short cycle where you hit 4,100, and then you get stuck 4,100, 8,100, 6,100, 2,100, back to 4,100. So these little cycles can occur way down the line. So you can have these long transients that convince you that you've made a good choice, but then actually you didn't make a good choice. So the middle square method was an example that was not a good use here. So, but it was simple to implement. It didn't take a lot of memory to do so. Difficult to choose a good seed. Typically degenerates to 0 or has short cycles. There are certainly other early PRNGs that have similar issues, middle product method and so on. So it wasn't really until we got to linear congruential generators that, now there's all sorts of really interesting random number generators, but this was the first one that seemed to hit the sweet spots. And so this was made random number generation practical. And this is what you've experimented with in the Unit C homework. And so the idea here in the LCG here is we've got these parameters, our seed, but it turns out the seed won't, if we choose the rest of the parameters right, we can choose any seed we want. And we've got a multiplier, an increment, and a modulus. And so given those parameters, every iteration, as you should probably know now by doing the homework, is just going to be the whatever the seed or the previous number was times the multiplier, add the increment, take that thing, do mod the modulus, and then that becomes your next number. And your output, your random number output, is just going to be whatever the current number is divided by the modulus. So our seed doesn't count as one of our random numbers, but we put the seed in and it generates, so we put x0, the seed in, x naught in, it generates x1, and then x1 will be the first number we use. We go on down through this. And so this is also called the mixed congruential generator, or the multiple, and if we, that's for the normal case when C is not equal to 0. If you get rid of C, it's the multiplicative congruential generator. This is also called a Lamer random number generator, Park-Miller random number generator. In this multiplicative case, basically getting rid of the plus allows you to calculate these things much faster, because remember, you're generating possibly millions of numbers all at once. So anything you can shave off the arithmetic is going to speed up your simulation. And then they've got inversive ones as well. So there are different variants of the LCG that are all were generated because the LCG sort of had early success. So the idea here is that the LCG is unfortunately very sensitive to choices of A, C, and M, but there are ways to choose A, C, and M to make it perform pretty well. The maximum period is the modulus, and if you choose your A, C, and M to have these properties, so the only integer that divides the modulus by C evenly is 1, A minus 1 is divisible by all prime factors of M, A minus 1 is divisible by 4, if M is divisible by 4. If you have those 3 properties, then you're guaranteed that the LCG is going to have a maximum period length. And so it will not generate a new number until you go the full modulus. So if it's a mod, if your modulus is 10,000, it will generate 10,000 numbers before it repeats. And that's pretty cool. So that's much, much nicer. I can put any seed I want in here. So that gives me 10,000 sequences. So I put a certain seed in, it gives me a sequence. I put another seed in, it gives me a sequence, and so on. And so yeah, if I know all of those sequences, I can start seeing the patterns amongst them. But in principle, putting in a different seed starts you in a different spot in that list of numbers, and it gives you these different patterns. So as my example here, I start with a seed of 27. This is just like the homework. I have A, C, and M set to 17, 43, and 100. So that ends up giving me a random number of 0.02. I take that 2, plug it back in, gives me a random number of 0.77, and so on. So pretty easy to apply, relatively cheap. And if I do that over and over again, here's an example where my modulus is 10,000. I didn't choose these, via the Hub-Dobble theorem. I just chose these kind of randomly. And it turns out I still get a 2,000 cycle period here. So I can see here that from 468, iteration 1 down to iteration 2000, I did no repeats. And it's not until 2001 it finally repeats. So I get relatively long cycles out of this. And they do have uniformity as well. So I get uniformity and independence out of, so the long cycles basically give me independence. The uniformity in long cycles doesn't always give you independence, but that's one of the necessary conditions for independence. And then the uniformity here, those are those same, a histogram of those same 2000 numbers looks pretty good. So that's the linear congruential generator. It still has short cycles relative to what we need for practical simulations, but we're on the right track. So any questions about that before I add one wrinkle to the LCG to extend its cycle length? So what I want you to remember is the LCG allows us to get uniformity and independence and allow us to use any seed that we want. But the LCG by itself has got relatively short cycles. Its cycles are limited to the modulus. And if you don't choose these parameters correctly, which are done for you by the developer, then you may not even get this full cycle length. But even that is not very long in terms of cycle length. All right, so if I want to extend the LCGs to have much longer, then I can do what's called a combined linear congruential generator, or a CLCG. And so this is a simple idea. I just basically take two linear congruential generators, add them together, and then mod the sum. So I've got these two generators, and you can imagine that if you look at these two generators here, this is an example from 1986. This has got a large modulus. This has got a large modulus that's a different length. So already I know that most likely this LCG is going to repeat at a different cycle length as this one. So now when I add them together, it's like generating a beat in music. I've now extended the cycle length to be longer than both of their cycle lengths because this one cycles at a different period than this one. So this sum is going to cycle at an even longer period. So, so this combined generator here has a period of 2.3 times 10 to the 18. So that's 2.3 with 18 zeros after it, or I guess 17 zeros after it, which is way longer than this period here. So that's pretty good, right? So, and so we got uniformity, we got independence, and we can, in theory, start with pretty much any seed we want, and we got these long periods. So a trivial example of what happened there. So this is, I just created a much simpler X and Y LCG and a combined one, X minus Y, combined LCG. And I can see that here, X has got a period of 4, Y has got a period of 3. So they start repeating pretty quickly. But when I combine them in this way, so here I subtracted and did mod 3, then the result here has a period of 12, which happens to be these two periods together. Again, kind of like a beat in music. So, so any questions about that? The idea of the combined linear congruential generator. This finally, with papers like these, this finally brought us to kind of modern random number generation, where we can now generate huge sequences of independent random variables. And what's also cool about these things is that if you look closely at the output here, not only do I have a long cycle, but I do get repeats of certain numbers, but the numbers that follow them are different. So it's like I can see I got a 1, a 1, a 1, and a 1. This one's followed by a 0. This one's followed by a 2. This one down here is also followed by a 2, but then that gets followed by another 1. So just so it starts breaking up these tight dependencies where so you don't start seeing like over here, you know, I see that like this 3 is followed by a 0, so is down here the 3 followed by a 0. So even though I get sort of uniformity there, I don't quite get the nature of independence that I want. So this actually makes a far more independent number string as well. All right, so any questions about the CLCG? Does that make sense? Okay, questions online? All right, so, and then yes, so now modern ones have even longer periods, so they're pretty big. All right, so what I want to end on here for today is I at least want to talk a little bit about tests for uniformity, and then we'll pick up where we, from here next time. So uniformity, like I said, we know this definition here. We want the output of a pseudo-random number generator be indistinguishable from numbers drawn from a uniform distribution. So statistically speaking, if we look at a bunch of numbers, we need to make an inference. Are these uniform or not? Well, we assume that they're uniform. That's the null hypothesis. And our alternative hypothesis is that they're not uniform. And so we need a statistical test that will look at these numbers and see how far away are they from the null. And that test is going to have a level of significance, which is the probability that we falsely reject uniformity. So how often is a uniform distribution or uniform output of numbers going to be, our test is going to flag as being non-uniform. And we want that to happen less than, say, 5%. So that's what we're saying here. So we have to think, what statistical tests can we use? And so, so you should get to a point where, like, so this is sort of the prediction that I want to work off of here. If the uniform distribution is divided into n subintervals of equal length, the expected count of each of those numbers should be n divided by n. So it should be equal across all over the subintervals. So I draw capital N numbers across little n intervals. And the number that lands in each of the little intervals should be approximately n divided by n. So I need a statistical test that acts on counts data, that compares expected counts to actual counts. Do you know from 380 what is a statistical test that is used for count data? It's not the t-test, because the t-test is on continuous data. What statistical test, and so it should get to the point where if anybody says, here's count data, here's expected counts, here's actual counts, your brain should go here immediately. So what's the statistical test we use for count data? It's a test though, like a t-test or an ANOVA. So what's a test that you probably did in 380 that it compares expected counts to actual counts? Any guesses online? Chi-squared online, that's what I'm looking for there. So that's the test that we think about here, is that whenever you see count, you should immediately think chi-squared. You know, they both start with C. And so the idea here is a chi-squared test compares the expected frequencies to observed test frequencies, but there are other tests we can use, like the Kolmogorov-Smirnov that used in the homework for small sample sizes. So that's what we're going to use the chi-square test for, is the test for uniformity. The idea here is we're going to divide our hypothetical interval into n classes of equal length. So on a midterm, I would just tell you how many classes. So I would say, do the chi, do a test. I may not tell you do the chi-squared test. I might say, let's use 4 intervals to test the hypothesis of uniformity for these numbers. And you, if I give you 20 numbers, then you would take those 20 numbers and you would expect that there'd be 5, roughly 5 in each of those 4 intervals. And that's kind of what we're saying here. So we take this entire 0 to 1 interval, we divide it into 4 subintervals. So like 0 to 0.25, 0.25 to 0.5, 0.5 to 0.75, and 0.75 to 1. Those are our 4 intervals. And we count the number of observations in each class. Now, the important thing is that if the expected number is less than 5, we can't use a chi-squared test. For reasons that we'll describe a little later in the semester, the chi-squared test is built on an approximation that requires you to have an expected number of counts to be 5 or more. If it's less than 5, you're really stuck with things like the Kolmogorov-Smirnov test. Now, once you've got that, you then, as you did in 380, you take the observed counts minus the expected counts squared divided by expected counts. We will talk about a little bit later where this funny formula comes from. And for a uniform distribution, the expected counts, again, are just going to be the total number of samples divided by the total number of intervals. And this will give you a statistic. And this statistic, like most other of these statistics, gives you a distance from the null. If the chi-squared value is high, if it gets sufficiently high, you'll reject the null. If it's small, you may fail to reject the null. So that's how you should interpret this. And if you look up at a chi-squared table, that's how you interpret is, is p less than 0.05 good or bad or whatever. Then if this is larger than the critical value in the back of the book, then it's very different because it's larger the critical value. And that means we reject the null. And that's a p less than 0.05. So that's just something to remember there. So I'll run through this example. This is where we'll start off next time. I don't want to rush through any more here, and this is a good place to stop. So let me jump to an attendance exercise. Say here, and put that. And the question I have for you is, what statistical test is associated with comparing expected counts to actual counts of events? So what is the test you should immediately think of when you hear the word count? Count data almost always means this test. And that's all I've got for you. So I hope you have a good weekend, and we'll see you Tuesday. for random variate generation. Any other questions online? In that case, I will go ahead and close the room. Have a good weekend.